it's time to start this workshop. Yeah, I'm Feng Lilin. On behalf of the local community, I would like to thank all the invited speakers and all the audience to come attend this workshop. So you know that now this is holiday. Today is holiday in this country, so I think it's good for people you can sacrifice your holiday to come. And I think this workshop is basically on topological order and the related recent development. And I think it's good to, in some sense, to grow with big idea. Especially we can learn from it, and also we can, the best scenario, we can also contribute to the development. And I think topological order definitely is the big idea. I learned this idea first about 20 years ago, also in this type of workshop in Beijing. And since then, we see that this idea evolved by itself, and also combined with many new development from the other topics, like quantum information, quantum field theory, quantum entanglement, and also other branch of condensed matters. Yeah. And I think it's good that we can have all the worldwide experts on this topic to come here and give their insight to this topic. And I hope that all you can get inspired by this series of lectures. And also, I take this chance to thank my co-organizer, especially Professor Jenny Hong and also Dr. Wang Yidun. Without them, I think we cannot make this workshop to happen. Okay. And also, I would like to take the chance to thank some local faculty, like Chen Junwei, he didn't come. Also Gao Yinze, and also Guan Xisen. I think they have give me the moral and also financial support for this workshop. And also, finally, I'd like to thank the NCTS and Academy Sinica. They provide financial support for this to happen. Okay, then we will start.
So begin the morning session of this workshop and school. The morning shop, we have two talks. The first one is given by Professor Zhengcheng from Parameter Institute. And he will be speaking about p+ip superconducting state emerging in two-dimensional strongly correlated Dirac systems. Let's welcome him.
It's my great pleasure here for this wonderful conference. And actually, it's my first time to Taiwan, so I was so impressed about the culture and the food, actually. So today, I would especially thank the organizer here, like Professor Lin Fenli and also Professor Janet Hong. Yeah. Okay, so today I try to talk about some generic way to make p+ip topological superconductor state, because people are interested in this kind of states for almost 10 years, starting from the proposal by Nick Reed as a potential resource for topological quantum computer. But so far there's no good material, even this kind of Lucent oxide, it's kind of still arguably kind of still not quite sure it's a p+ip superconductor or not. So I also would like to thank my collaborator Hongchen Jiang from UC Berkeley, but he just moved to Stanford as a scientific staff, and also Professor Bhaskar from India and Permitting Institute. Okay, so so the particular problem I want to address actually is kind of a pretty old problem. Just like we try to ask whether the so-called Nagorka state. So people probably, some people doing condensed matter physics might understand this Nagorka state. It's kind of just a very simple, fully polarized state. But it's very surprising that usually in Hubbard model, if you just dope one hole and push this U to the extremely strong coupling limit, U equal to infinite, let's say, and the Nagorka like almost 50 years ago, first proved the true ground state is a fully polarized state. So this is kind of very surprising result. And so today I'm basically trying to talk about what happens if we dope the system, not just one hole, with finite density of holes. And I will show that this Nagata state is actually unstable, and some very interesting p+ip topological superconductor will emerge. But the method I want to apply, first I will try to apply this numerical method, the so-called Grassmann tensor product state, as a kind of variation approach for strong probability system. And also, I will try to develop some controlled quantum field theory to understand the underlying mechanism. And it turns out pretty interesting that in such kind of ferromagnetic ordered state, this ferromagnetic skirmion can serve as a pairing force. And so I call it a mechanism of skirmion current pairing. And also I will propose some interesting kind of experimental material. Probably in future people can try to realize this p+ip superconductor in a large class of material. And finally, there's a summary and outlook. Okay, so let me just briefly review the story of the p+ip, the so-called p+ip superconductor in spinless fermion. So when we talk about p+ip superconductor, we usually think about it's related to Nick Reed's original proposal, which just simply prove if we solve the BDG equation in a spinless p+ip superconductor, the vortex core will trap a single Majorana zero mode. And from some very advanced kind of mathematical theorem, you can show that such kind of p+ip vortex core basically is non-abelian anneal, and more precise, it's Ising anneal. But here I want to emphasize this spinless nature because in some p+ip superconductor like this Strongsen-Rosen oxide, basically it has spin. So even you realize that kind of p+ip superconductor is not really useful because we want to spinless just one component, not two components. And due to this kind of purpose, we think that so far there's no successful candidate to realize Nick Reed's proposal, which is kind of very important. But unfortunately, in our nature, most electron carry spin, and there's no way to find a spinless electron. But of course, one may think about there could be some naive way to realize it. For example, we can just add some very strong magnetic field to polarize electrons. But unfortunately, in usual BCS theory, if you apply very strong Zeeman field to polarize electron, the BCS state is unstable, and usually it's towards a phase separation or some FFLO state. So there's no way to get a p+ip state. Okay, but we never think about what happened in the strong coupling limit. So today I just want to think about this problem in an extremely opposite limit. If we turn on strong coupling, whether this kind of p+ip superconducting state might be even kind of natural and stable than the usual S-wave-like state. Okay. So the particular model I want to address is actually very simple, just the standard Hubbard model. So I assume here people doing kindness matter may be familiar with this Hubbard model. And if we do second order perturbation, we can kind of simplify it as a TJ model. And this J is just 4T square over U. Okay, so I want to also choose some interesting geometry I will explain some reason that if we study the Hubbard model on square lattice, maybe not as interesting as Honeycomb lattice. So today I will focus on Honeycomb lattice. But the Nagata theorem basically kind of the same for Honeycomb and square lattice. Basically, Nagata stated 50 years ago, for any kind of bipartite lattice, if we dope one hole, then the state must be fully polarized. And the underlying physics is actually very interesting because it's not a usual ferromagnetic order, because if you dope one hole in the infinite U Hubbard model, basically if there are kind of downspin, the hole very hard to move because the fully polarized state is kind of eigenstate of the infinite U-Hubbard model. But it turns out if we dope one hole, it's not only an eigenstate, it's also a true ground state. And if everything is polarized, there's no frustration, so this hole can kind of move freely and gain kinetic energy. Because if you for this U infinite, basically it's J equals 0 limit, so the Hamiltonian is extremely simple, just a one term. So for this one term, the Hamiltonian, this ferromagnetic order actually is we call the kinetic energy driven because we only have kinetic energy. There's no other terms, so extremely simple. So the infinite U is a very important starting point because if we want to study weak coupling, usually we're starting from the point like U equals 0, which is Fermi liquid. But if we want to have a controlled understanding about the strong coupling, it's better to think about we start from U infinite and then we push back to the finite U. So most of my talk will focus on the U infinite limit. And I will also discuss the interesting physics that happen at finite U. So it looks like Nagorka's theorem very promising to solve strong coupling limit systems. But unfortunately, for almost 50 years, people try to make effort to improve Nagorka's theorem. So people can generalize into a couple of holes, but still finite number of holes. So in the thermodynamic limit, its doping is still 0. So it's really hard to generalize the theory to some finite density of holes in the thermodynamic limit. So, but in the last 10 years, this development of the tensor network state make this kind of study might be possible. And based on the variational results, we also develop effective field theory to understand the underlying physics. Okay, and also I want to mention that in some infinite U-Hubbard model, if you add in some Zeeman field, assume the Zeeman field is extremely large, let's say infinite, then this Nagorka state always stable because at finite doping, this fully polarized state is still eigenstate. But it's not necessary to get true ground state, but if you add infinite kind of large Zeeman field, it becomes kind of true ground state. And then you can think about in a realistic system, if we reduce this Zeeman field, maybe some phase transition can happen and enter to some interesting new states of matter. There are some interesting results, previous results on this square lattice system. So for square lattice Hubbard model, K. Wilson's group actually studied this problem 2 years ago. And their claim is that up to 20% doping, the fully polarized Nagorka state is stable. And then there's instability towards phase separation. But these results only rely on the kind of a couple of chains, so it's still kind of one-dimensional result. And this kind of Nagorka state, the stability might be tied to this one-dimensional geometry. And we also try to check this square Hubbard model in our recent work. But today I try to choose some different geometry. So basically the simplest 2D lattice geometry, the honeycomb lattice. And the reason we are interested in honeycomb lattice because first that half filling is also bipartite lattice, so it's also kind of antiferromagnetic order if the U is finite. And most importantly, because this kind of geometry effect, it's very easy to argue if we have some pairing channel, it's naturally favor D plus ID or P plus IP. Because people may understand that on square lattice, the favorable pairing symmetry is kind of D wave. But because this is a geometrical twist, you cannot have a D wave. D plus ID is much more natural. But another important thing is that D plus ID and P plus IP, this angular momentum part completely the same on the hexagon lattice. Basically, when you twist this superconducting order parameter along these 3 directions, there's 2 pi over 3 phase shift or 4 pi over 3, but basically they're the same. Right? So that's the reason that if we try to realize some topological superconductor, it's much natural on honeycomb lattice instead of square lattice. Okay, so and for some other interesting, a few years ago, people proposed that if the Hubbard U is not extremely large, like around U of t around 4, there could even be spin liquid. But this kind of statement still needs to be further tested. And also, there are actually interesting material can realize the Hubbard model on honeycomb lattice, just not as familiar as square lattice. So for future experiments, maybe this is also very interesting. So the strategy of this talk, we try to first perform some numerical calculation, and then we go to this analytical understanding for the underlying physics. Okay, so this kind of numerical approach is not the standard numerical approach. It's called a tensor product data state. So I assume here people not familiar with about this kind of technique. So I want to give a brief introduction about what is tensor product state. So everyone may be familiar about the so-called mean field approach for many-body physics, because mean field theory is kind of very powerful and has been used for almost a century in condensed matter physics. So what's the essential feature of a mean field? Mean field is too simple. It's very, very simple. For example, for a spin 1/2 system, we can just associate some spin up configuration with a complex number u up, spin down configuration with a complex number u down. And when we're talking about mean field state, we actually means that the wave function just a product of some complex number for on any fixed Ising basis. For example, we have Ising basis, some configuration up or down, up or down, up or down. Then here just u up, u down, u up, u down. You just multiply all this complex number, you're gonna get a coefficient. So the coefficient is a wave function. But also from this kind of figure, you see it's kind of pretty classical, and there's no entanglement at all. It's kind of like a semi-classical approach for a quantum system. There are only quantum coherence on a single site, but between different sites, there's completely no quantum entanglement at all. So that's why it's not a surprise that it fails for generic strongly correlated systems. So in 1D, there are much better improvement based on the idea of the so-called density matrix renormalization group. And also, people realize that the so-called density matrix renormalization group actually equivalent to a special class of this variational wave function, the so-called matrix product state. So if we look at this kind of picture, you think about it's pretty straightforward. Because this complex number has not so much information. So we just replace the complex number to a matrix. So this matrix, typically you can choose it to be some D by D matrix. So all these D square elements could be variational parameter. But then for up configuration, we have A up. For down configuration, we have A down. And in total, we have 2D square variational parameter. So the wave function is also very simple. Just you make a matrix product and take a trace on periodic boundary condition. And on open boundary condition, you can put some boundary vector to contract and write on this trial wave function. So in terms of this picture, I just draw some like rank 3 tensor. Because this vertical one, usually people think about it represents the physical degree freedom. So you can choose up or down. So the horizontal one is the so-called internal degree freedom. So it's dimension D. And in this figure, it's a convention in this kind of study because this figure is much easier than this formula. So the figure, when we connect this two horizontal legs, we just make a trace with respect to this canonical delta function, we just sum over these internal indices. So if on the periodic boundary condition, you can also think about you can trace over the very left and very right. So finally, this holds just a number. And in terms of this kind of figure, it's very hard. It's very easy to generalize into higher dimension as well, because in 1D we only have 2 directions, left and right. But in 2D, if you think about you have some square lattice, you naturally have 4 directions. So you not only have left and right, you also have up and down. So this vertical indices always represent the physical degree of freedom. So basically, you can think about we have instead of have 2 complex matrix, now we have 2 complex tensor, right? So we have more kind of variational parameters here, and we have T up and T down. Okay, so in this kind of picture, it's also very obvious that when we connect these internal legs, we just sum over the internal indices. So finally, in a periodic boundary system, we just sum over all the internal indices. just leave this physical indices open. And once we fix the physical configuration, just a number. So this number is the wave function we are looking for. Okay, so this is the basic structure of this so-called tensor product state. And during the past 10 years, actually it's right 10 years after the first proposal by Frank Rostrip and Dirac. So because they first proposed by these quantum information people, so they have a pretty kind of informational explanation why such kind of answers could be good. Basically, there's a long time conjecture that the ground state of certain gap Hamiltonian will satisfy this so-called area law. So they can show such kind of construction naturally will satisfy this area law. So this can be understood in the following. We can just think about this so-called tensor product state. It's some generalization of projective wave functions. We're starting from some so-called internal degree freedom. So this internal degree freedom, sometimes you can think about just like the slave particle. You define in the auxiliary space. And in the end, you want to project back to the physical space. So in this kind of construction, each physical site is split into 4 subsets. So the nearest neighbor subsets just form a maximal entangled state. So sometimes people in quantum information call it GHZ state. And it's nothing, just a kind of equal with the superposition of all the possible configurations on the 2 sides if the configuration are the same. So it's kind of some short-range RBB. You can also think in that way. So so the parent state is pretty simple, just the product state of this short-range RBB. But then you can make a projection. So the projection just defined in the following way. Actually, the tensor is a projection. So you're kind of acting on the internal state labeled by left R up down, and you map to the physical state. And in the 1 dimension, actually this is pretty kind of obvious, like for so-called this AKLT state with projection, just the usual projection to the maximal symmetric state. Okay. So from here you can see that the original kind of parent state satisfies this area law, but here you make a projection, so you can not have any kind of things beyond the area law, because here you after projection you get actually a less degree of freedom. So sometimes there could be a subtraction from area law. So people call it the so-called topological entropy. And it turns out such kind of construction is pretty successful to classify topological phases. For example, it can classify the so-called non-chiral topological order in 2+1D, and can also classify this so-called symmetry protect topological order in 2+1D. And in some realistic model, we also tried some variational approach for example, like a J1, J2 model, or some spin 1/2 Kagome lattice Heisenberg model. And it turns out all these results are kind of pretty good agreement with the current DMRG calculation. And also, for some system, we also investigated this topological phase transition, which is also in agreement with the fundamental result for those models without sign problem. So based on this kind of result, we kind of think about such method might be trustable for strongly correlated system. And we try to generalize this kind of method into fermion system as well. But for interacting fermion system, there are some more subtle issue. And first is that how can we define a wave function for interacting fermion system? And from the usual perspective, we know that if we want to define a wave function for interacting system, fermion system, we must have a particular ordering of the fork bases, right? So for example, we have 1, 2, 3, 4, 5, 6, 8 in this kind of snake-like path. And then we can write down the wave function. But then, if we think about the fork basis, it's not just like a spin configuration. You cannot just think about there's no fermion just a 0, one fermion just a 1, because there's a non-trivial sign due to this anti-commuting property of this fermion creation operator. And if you, for any kind of given path, if you think about hopping from 1 to 2, it's just a very usual kind of hopping matrix element. But if you have a hopping from 1 to 5, actually this hopping matrix element could be either plus or minus, which is dependent on this fermion parity on this path. So that's why you turn to this complex fermion operator into a hardcore boson operator. You always put some like Jordan-Wigner minus 1 of a sign there. So this kind of property makes it very difficult to think about tensor product state for a fermion system, because we think it's easy to see that even for a fermion system, the wave function in certain fork bases, the Hamiltonian for hopping term is non-local. It's a completely non-local system. That looks like extremely hard. And also, we will easily to see that there's obstruction, because for any kind of given configuration, for example, we claim there's like 0 fermion here, 1 here, 1 here, and 0 here. But then we will ask what's the ordering on these sites. If they reorder the sites, obviously we must get a minus sign for the fermion wave function. But in this usual definition of tensor product state, there's no fermion sign. So you can naturally ask, so this wave function corresponding to what kind of fork basis ordering, right? So because there's no resolution for different fork basis ordering, so obviously this kind of wave function is not suitable for a fermion system. Yeah. Okay. So to understand this, how to define this wave function for a fermion system, we want to generalize this concept of complex valued wave function into so-called Grassmann valued wave function. And also in Dirac's work, they propose some different way called this so-called fermionic taps. But basically, these two methods, they are equivalent. So the idea is that when we define some wave function under this fork basis, there's naturally kind of a sign structure. If we reorder in the basis, we must get a minus sign. But how to keep track of that minus sign? The idea is actually very simple. We just put some Grassmann variable in the wave function. And this Grassmann variable can help us to keep track of this minus sign. So the only kind of complication is that now, for the internal space, this ABC is the kind of in-plane leg, the internal kind of degree freedom. So here, in order to study honeycomb system, now I changed geometry just to honeycomb system. So for this internal degree freedom, ABC, we naturally split into two kind of channel. I define an integer function. This PA take either 0 or 1, just like a fermion parity. It's 0 means no fermion, 1 means 1 fermion. So when it take the value 0, there's no Grassmann variable attached to this tensor. But if it's 1, there's a Grassmann variable attached to this tensor. So this physical degree freedom, just the usual kind of configuration basis for fermion. Let's say for m equal to 0, there's no fermion occupation. If there's a 1, means there's a 1 fermion occupation. Okay, so this Grassmann algebra may be people also familiar, but let me just remind you that the rule is that theta, they just anti-commute. And if we integral over d theta, theta is just equal to 1 if they are the same. Otherwise, it's 0. And if we integrate d theta over nothing, it's just 0. So that's just a very formal algebra. But the point is that this kind of algebra will keep this sign of a fermion system. And then when we generalize this kind of metric tensor into its corresponding Grassmann version, it's not usually canonical data function. You also split into two channels. If PA equals 0, just the usual kind of canonical data function. If PA equals 1, then there's a pair of this kind of Grassmann metric. It's like a d theta, right? Okay. Because when we define this fermion wave function, we always need to kind of integral over this Grassmann number. So this d theta and theta must appear in pairs. So that's why we need to put d theta on the metric and the theta on the tensor. But we also need to impose a constraint, which is crucially important. The constraint actually just want to make sure that the total fermion parity in the internal space must be the same as the fermion parity for the physical space. So this is a crucial step, because if you think about if okay, I have 0 fermion, then I always have even amount of Grassmann variable here. If I